Let's talk about the wave-particle duality of nature. Just as light can have both wave properties and particle properties, it can behave just like a wave or it can behave just like a particle. Those two extremes. And we can predict how it's going to behave depending on how we measure in the experiment that we set up. With life-size objects, things that we can hold in our hand and see and touch and throw around, they behave like particles. They're too big for us to detect their wave-like character. However, for particles on the subatomic scale, protons, electrons, and atoms, they are small enough that they behave, that we can detect their wave-like character. So they behave similarly as particles and waves. So an electron moving is a particle, but it also can behave just like a wave. And we use its wave-like properties when we build an electron microscope. A physicist named Broglie came up with the Broglie Relationship. And it gives us the break form of the relationship between wavelength and momentum of a particle. So the Broglie relation is the momentum is equal the momentum of a particle is equal to Planck's constant divided by its wavelength. So another way of writing this is momentum times wavelength is equal to Planck's constant. So here's Planck's constant again. It's a constant of nature that arises frequently in the study of small particles. Let's review what momentum is. Momentum is just equal to mass times the velocity of a particle. Now momentum is a vector because velocity is a vector. It has both magnitude, speed, and direction, which way you're going, north, south, east, west. We're just going to use the scalar nature of momentum, and so we'll just consider it in one dimension, and we will just get the scalar value, just meaning the number value for the magnitude of momentum. We'll just have it mass times the speed, and so when we say v, velocity, we're using speed, just the magnitude. Okay, say we have an electron. We use the symbol E negative to symbolize an electron. So we have an electron and it's traveling 1/4 the speed of light, c. And let's find its wavelength associated with it. So the wavelength is equal to Planck's constant divided by the momentum from the Broglie relationship, just solving for wavelength. So that's h over the momentum, which is mass, times speed. So our speed is 1/4 the speed of light. So this will give us 4h over the mass times the speed of light. So now I'll plug numbers in. So lambda is 4 times Planck's constant. Divided by the mass of the electron, and you can find it in a table. I hope I remembered that correctly. And then multiplied by the speed of light. 3.0 times 10 to the 8th meters per second. Now numerically, this will give me 9.7 times 10 to the minus 12th meters. Now let's see how the units work out. I'm going to leave the numbers out and just look at the units. So I have joules times second divided by kilograms times meters per second. So this will give me joules times second squared over kilograms times meters. So I've taken the compound fraction, moved it into the numerator, and then the seconds, that is, and then a joule is a kilogram meter squared per second squared. Okay, so now we see the second squared cancels, kilogram cancels, one of the meters cancels, and I'm left with meters. So that's how the units work out. So we need to put joules in its derived units in order to get all the units to cancel to give us meters.